Okay, so curl can be defined in two ways. Well, it can be interpreted two ways. So way number one is that it's a measure of the rotation of a vector field. The second interpretation is curl can be used to test whether or not a vector field is conservative. Okay, so if you're asked to find the curl of a vector field that looks like this, and it doesn't matter that we don't have a formula for the vector field. I'll show you how to evaluate it in a minute here. You can imagine that if you were to put a stick or something in the middle of this vector field, imagine this vector field was like a velocity field of fluid or something like that. You can imagine that if this is where you put the stick at t equals 0, then you can imagine that at some time t later, this stick is just going to be sort of translated in this direction to some other time, or it's going to be translated in this direction to some other point, but it's not going to rotate at all either way about any axis. Okay, so that would mean that for this particular vector field, the curl is 0. Okay, so this is how you calculate curl of a vector field. So if f is a vector field and you want to calculate its curl, also I should also note that maybe that example that I just did wasn't the best example, but I'm not sure if there are higher dimensional forms of curl, but this form of curl that I'm going to show you here is only for 3-dimensional vector fields. Okay, so if you want to find the curl of a vector field, it has to be a 3-dimensional vector field. So the curl of f can be written like this, where it's the cross product between this differential operator here called del and your vector field. Okay, so you should know that when you take the cross product of something, you're going to end up with a vector. Okay, so when you take the curl of a vector field, you're going to end up with another vector field, where this little upside down triangle, this is just notation, and this actually can be thought of as a vector that looks like this. Okay, so when you calculate curl, you literally take the cross product of this vector with your vector f. So when you take the cross product, you write it like this. We'll say that f is the vector p, q, r. Okay, so when you work this guy out, you sort of ignore this first column and this first row, and you take the subdeterminant here, so you take the partial of r and you subtract the partial of q. So the partial of r with respect to y, subtract from that the partial of q with respect to z, and that will be in the I hat direction. When you do the j component here, it's the partial of r with respect to x, take away the partial of p with respect to z in the j hat direction, and lastly in the k hat direction, it's this guy here. Okay, so I'll just do a quick example. Let's say that f is going to be the vector, let's make this up, x squared y, z x y, and x squared y cubed, z to the 4. Okay, so if we wanted to find the curl of f, then what do we do? Okay, well, here's our little determinant here to help us out. So in the I direction, we would have the partial of the z component here with respect to y. Okay, so it would be the partial of this guy here with respect to y, so that would be 3 xy squared, and then we would subtract from that the partial derivative of the y component with respect to z. Okay, so that would be this guy right here. So we have something like that, and that would be in the I hat direction. For the j component here, we'd have the partial of the z component with respect to x. So that would be this guy here. 2xy cubed z to the 4. And then we would subtract from that the partial of the x component with respect to z. So that would be 0. And then for the k component, we would have the partial of the y component with respect to x. So that would be the partial of this guy with respect to x. That would be, and then we would subtract from that the partial of the x component with respect to y. So partial of the x component with respect to y. So we can tell right off the bat that the curl of f does not equal 0. So that means that this vector field is not a conservative vector field. Okay. Remember, if you were to compute the curl of a vector field and you were to find that it was conservative, then you would be able to use the fundamental theorem of line integrals in order to simplify things when evaluating the line integral. So it's a quick example. Okay, so what about divergence? If we had a vector field that looked like this, so if you were to put a balloon in here with that contained a certain amount of mass, and this vector field was fluid flow, and you could see that, like, you could imagine that if the fluid was entering this balloon, you could see that, like, at some time later, this balloon might look something like this. Okay, where the mass of the balloon in this fluid flow actually increased. Okay, so again, there's two ways that you can sort of interpret divergence. One, it's the net rate of change of mass, and two, you can see that all of these vectors here seem to be like diverging from, say some point x, y, z in this vector field. Let's say this is a three-dimensional vector field, whatever. Okay, so divergence is also measures the tendency of a fluid to diverge from a single point. Okay, so if you were to calculate divergence, sometimes divergence is written like this: div f, where in this case f doesn't have to be a three-dimensional vector field. Okay, so I guess I could have just said in this case the point x, y, and left out this z term here. It doesn't necessarily have to be a three-dimensional vector field, as does curl, but for divergence it doesn't matter. So divergence is going to be the dot product of this del operator with your vector field. Okay, so again, this vector up here is del. Okay, so I mean, it's not a real vector, it's just notation, but you can think of it, it helps you remember how to compute this, okay, rather than like remembering formulas. So it's basically the dot product between this vector and your vector field. And since this is a dot product, you end up with a scalar answer in the end. Okay, so again, if the divergence is 0, it means that your vector field is just purely translational. Nothing is diverging. So if you were to pick a point in your vector field, nothing would diverge from that point. Your point, or another way to think of it is if you were to put a balloon into a vector field that has a divergence of 0, then your balloon wouldn't increase in mass. Your balloon would just be translated. So maybe if you had another vector field, so if you had another vector field like this, and you were to place a balloon somewhere in that vector field at some time t0, then at some time t1 later, your balloon would have been translated, but didn't increase in mass at all. So the divergence is 0. And this is the same vector field I use in an example of curl, where curl was 0, so this vector field has no rotation and no divergence. It's just purely translational. Okay, so I'll just do a quick example of divergence. So, obviously if your vector field was like, of n dimensions, then you would have like this del operator would be partial x1 as the first component, partial x2 second component, dot 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 partial x to the n, or sub n, for the nth component of the vector. And then for f you would have n components. So this you can calculate the divergence of like an nth dimensional vector field. So here I'll just find the divergence of e to the 2, something like this, just a two-dimensional vector field. Okay, just something like this, whatever. So if I wanted to find the divergence of this guy, all I do is take the partial derivative of the first term with respect to x and add it to the partial derivative of the next term with respect to y. So the partial derivative of this guy with respect to x would be 2y e to the 2x, and then the partial of this with respect to y would be, well, I'd have to use the product rule, so I guess I would have x squared e to the xy plus x squared y root x cubed. Okay, so the reason I'm talking about curl and divergence now is because Green's theorem, Stokes' theorem, and the divergence theorem all include this kind of notation. So I think in video 9 or something like that, when I first talked about Green's theorem, I wrote a bunch of different ways that Green's theorem can be written. So I'm going to write them again, and with this notation, just so you can see how it's used. So Green's theorem says that the line integral of a vector field around a closed loop is going to be equal to the double integral of, well, what did I say before? I said that if f is a vector field defined like this, then it's going to be the partial derivative of the this component here with respect to x minus the partial derivative of the p component with respect to y. Okay, dA over the region bounded by the curve C. Okay, so you can sort of see in here that when you're computing curl and you're finding the component of curl in the k direction, you take the partial derivative of q with respect to x and you subtract from that the partial derivative of p with respect to y. Okay, so another way that can be written is the line integral around the closed loop is equal to the double integral over the region bounded by the curve C of the curl of f dotted with k hat dA. Okay, so what happens when you calculate this guy here? Well, you're going to have something like this. Okay, where you write the vector f as having a 0 in the component that points in the k hat direction, and since when you take the cross product of two vectors they have to have the same number of components, you would also put a 0 in the k component of this del operator vector here. It's not really a vector, but so if you were to calculate this, you could see that the component in the I hat direction is going to be, well, 0 minus 0. The component in the j direction is going to be 0 minus 0. And then the component in the k hat direction is going to be exactly what we wrote up here. 0 in the I hat direction plus 0 in the j hat direction plus that guy there in the k hat direction. So then when you take the dot product between this guy and this unit vector, what do you get? Well, you're taking the dot product between this vector that I just wrote up here, 0, 0, q sub x minus p sub y, and you're dotting that with a unit vector in the k hat direction. So what does it mean to be a unit vector in the k hat direction? Well, that means that you have components 0, 0, and then 1 in the k hat direction. You have a magnitude of 1 unit vector. in the k-hat direction. So obviously when you take this dot product, you have 0 times 0 is 0, plus 0 times 0 is 0, and then you just have this term here multiplied by 1, which is exactly what we have here. Okay, so this is actually how I remember Green's theorem. Okay, and there's another way to represent Green's theorem where you use the divergence theorem, or use this type of notation here, in here somewhere, to change this a little bit. I'm not going to talk about that right now. I'll probably mention that again once I talk about the divergence theorem, and then I'll show how Green's theorem relates both to Stokes' theorem and the divergence theorem. So anyway, thank you very much for watching.